Hi everybody, here's what we would have been working on today if they hadn't canceled our class. We would have just been doing a review of the first derivative test, which helps us figure out if functions are increasing or decreasing and if they have any relative maxes and mins. So let's look at example number 1. The key thing to consider when we're doing the first derivative test is we need to be looking at the derivative and setting it equal to 0 to find critical points. Sometimes I give you the derivative and you can just go ahead and set it equal to 0. Sometimes you have to find the derivative. In example number 1, you need to find the derivative. So let's find h prime of x, where we're just going to use the power rule. So negative 3x squared plus 6x, and then the derivative of 9 is just 0. To find the critical points, we set the derivative equal to 0, and then we can use our solving strategies like factoring to solve. So in this case, I noticed that there's some greatest common factors that we can take out. We can take out an x because they both have x in common, and we can take out a 3. I'm actually going to take out a negative 3 because I think that'll make some of my solving easier later. So negative 3, when you take negative 3, I meant negative 3, x. When you take negative 3x out of negative 3x squared, you're left with x. When you take negative 3 out of 6x, you're left with negative 2. You can check and make sure that if you distributed, you'd end up back at the original, which we would. Okay, now zero product property. We set each factor equal to 0 and we solve. So negative 3x equals 0 when x is 0. X minus 2 equals 0 when x is 2. So those are our critical points. Those are what we put on a number line to test for maxes and mins. So I'm going to put 0 on a number line and 2 on a number line. I've gotten a couple questions about where do you plug these values back in? Do you plug back into the derivative or do you plug back into the original function? We want to plug back into the derivative because we want to see if the slope is positive or negative to see if the function is increasing or decreasing. So we need to plug in something to the left of 0, so maybe negative 1. I like plugging it back into my factored form because I don't really care about what the answer is. I just care about if it's positive or negative. So if I plug in negative 1, I get a positive times a negative, which is negative. If I plug in something between 0 and 2, let's do positive 1, I get a negative times a negative, which is positive. And if I plug in something bigger than 2, like 3, I get a negative times a positive, which is negative. It's asking me on which intervals is h decreasing, so I'm looking for where h prime of x is negative. And then also I did learn, I kind of thought that the sign chart would be enough of a justification, but I did learn that we do need to justify in words why h is decreasing where it's decreasing. So the best solution for this one is h is decreasing on the interval from negative infinity to 0 and also from 2 to infinity. You could use inequalities if you wanted also. You could say something like x is less than 0 or x is greater than 2. But we do need this extra justification where we say because the derivative is negative there, because h prime of x is less than 0. So it turns out that College Board is looking for that justification for you to explain. Then it's looking for where does h have a relative maximum or minimum. So I'm going to go ahead and draw my little slopes in. Negative slope, positive slope, negative slope, because it helps me visualize whether there's a minimum or a maximum. So I'm looking at where x is 0, and I can see that the little slope graph that I just drew makes it look like a minimum. So we'll say h has a relative minimum at x equals 0. And then here's the justification part again. Because, and then this is the part where, again, it turns out we do need this. Because h prime of x changes sign from negative to positive. Let's do the same thing for the maximum. H has a relative max at x equals 2 because h prime of x changes sign. Now go back to your sign chart. What's happening at x equals 2? It changes sign from positive to negative. So even though all that information is in our chart, it turns out they do actually want us to state that in words. So that was example 1. I gave you a function. You had to find the derivative and set it equal to 0 to find the critical points, and then we had to make a sign chart with our critical points to see where the function was increasing or decreasing and to see where the function had a relative max or min. Now let's do an example that's a visual one from a graph. So I'm going to go ahead and still make a sign chart, even though I have the picture right in front of me. My critical points, let's see. First we have to see, is this a graph of the function or a graph of the derivative? It's a graph of the derivative. My critical points are at 0 and 4, because those are zeros of the derivative graph. I'm also going to put 7 on my sign chart because that's the endpoint. It says we're looking on the interval from x between 0 and 7. So all I'm looking for is whether the derivative graph is positive or negative here. So there's nothing in the graph to the left of 0, so let's start between 0 and 4. The derivative graph is negative. And then between 4 and 7, the derivative graph is positive. And then I'm going to draw in my little slope graph again to see that, yes, in fact, that is a relative minimum that's happening at 4. So we can say f has a relative minimum at x equals 4 because, here's the justification part again, we just needed to know that the sign of the derivative changes from negative to positive. So because the sign of f prime changes from negative to positive. Doing a little bit of abbreviation because I don't have a ton of room. All right, part B, is f increasing or decreasing at x equals 2? So let's see what's happening at x equals 2. Well, the graph of the derivative is negative at x equals 2, so we've learned that when the derivative is negative, that means the original function must be decreasing. So we can say f is decreasing at x equals 2. Here's our justification again, because the derivative is negative. And then part C is just a little bit of a fun extension. There's a transformation of the function. So it says, let's say g of x is f of x minus x. So we have to, it's asking where is g increasing, so we need to find the derivative. So the derivative of g is the derivative of x, of f of x, I mean, minus the derivative of x, which is just 1. So picture this whole graph that we were just looking at. The derivative of f of x graph is just going to be shifted down 1. So now all of a sudden 4 isn't going to be a 0 anymore. It's going to be down at -1. But this point here at 5 is actually going to be a 0 now if you shift the graph down 1 unit. And so is this one. So let's make another sign chart. Let me move that down a little bit. Okay, I'm still going to put a 0 on my sign chart, even though it's not a critical point anymore, because it's still the end point of our region. And then I'm going to put 5 and 7. And the graph between 0 and 5, the derivative graph is going to be negative. The graph between 5 and 7 of the derivative is going to be positive. So when we're looking for where g is increasing, it's going to be increasing where g prime is positive. So that's between 5 and 7. So we can say g is increasing on the interval from 5 to 7, and then we need our quick justification. Because the derivative is negative there. So that was just a little extension on what we were doing in the first part, where we had to take the graph and shift it. All right, this last part is a calculator one, so I'm going to pull up Desmos real quick, and we'll graph this function on Desmos. Where's my mouse? All right, let's go to Desmos, graphing calculator, And I could call this y equals or f of x equals. I can't call it f prime of x, though. It'll give me an error. So y equals 3 minus, and then I kind of liked as a little shortcut for the square root button, I like to just type SQRT, and it puts a square root on there. X squared plus x plus 4 cosine x. So here's what my graph looks like. It says we're looking for a local maximum on the graph. So we are concerned about our critical points. So this is the graph of the derivative. We want to see where the derivative equals 0. So the derivative equals 0 there or there. So those are really my only two choices. If you look at the multiple choice options, those are options A and D. The other options actually come from if you accidentally thought that this was the graph of the function and you were looking for a maximum, there's where the x equals negative 2.161 comes in, and there's where the x equals 1.494 come in. We don't want the maximum and minimum of the derivative graph. We want to know where the max and minimum of the original function are, so we need to know where the derivative is 0. So those are our two choices. So I'm going to put them on a little sign chart again and see which one of them is the local maximum, because that's the one that we're looking for. So on my sign chart, I could go negative 3.961 and 3.140. And then I'm going to just look at my graph instead of plugging stuff in algebraically. I'm going to go back to my graph and say, where is that derivative graph, positive or negative? So to the left of negative 3.96, it's negative. And then in between those two critical points, it's positive. And then after the 3.14, the graph of the derivative becomes negative again. So I can go negative, positive, negative, and then I can draw in my little slopes again to see which one is the maximum that I'm looking for. So the one that's a maximum is D. All right, so that was the review part. The last thing that we were going to do today is a little preview of what we'll be doing next, which has to do with the second derivative. So there's a whole bunch of questions just to kind of get at the thinking involved in that. So the first question is f increasing or decreasing at x equals negative 2? And the important thing is this is the graph of the function, not the derivative. So f is increasing at negative 2. You can see that the slopes of all the little tangent lines at different points are given, and the slope of the tangent line at negative 2 is negative 7. So f is decreasing at x equals negative 2. F is decreasing at x equals negative 2. Here's where the justification part comes in again, because the slope of the tangent line is negative. Or if we want to use our calculus notation, we could also say because f prime of negative 2 is less than 0. Okay, here's where the calculus part comes in. Is the derivative decreasing at negative 2? We know that the derivative is negative, but what about is it decreasing? So I think it might be helpful to look at what the derivative, what's happening to the derivative, the slope of the tangent line at all the values around negative 2. So the slope of the tangent line at negative 3, according to my graph here, is 2. The slope of the tangent line at negative 2, that's the part that we were just focusing on, is negative 7. The slope of the tangent line at negative 1 is given to be negative 10. So when we're deciding if f prime is increasing or decreasing, we kind of need to look at the slope of the slopes. So the slopes of the tangent line are decreasing. So f prime of x is decreasing. That actually tells us if f prime of x is decreasing, then f at x equals 2, f double prime of negative 2 is going to be negative, because it's like the slope of the slope is negative. So f prime of negative 2 is less than 0. And let me erase the markings that I already made, because it said we could actually use these tangent lines to kind of make a sketch of what the graph would look like, because the tangent lines tend to follow the curve pretty closely. So if I kind of use the tangent lines to trace my curve, That's what my graph is going to look like. And then just kind of an interesting thing to notice is all of these tangent lines, the first batch between -5 and -1, all of these tangent lines at all these points are above the graph, but then all of a sudden at -1, after -1, all of the tangent lines become below the graph. So that relates to something that we're going to learn about in the next class. So tangent lines are above the graph, but here in this interval, all of the tangent lines are below the graph. So this is going to be something that we're going to be studying in the next section, but just a little preview of it is we're going to be looking for where the graph is concave up or concave down. Hopefully that's a term that you learned about either in Algebra 2 or in pre-calc, but that pink part of my graph is concave down. If you poured water into that section of the graph, the water would spill out of the graph. It's concave down. The yellow part of the graph is concave up, where if you filled it with water, the water would stay in that part of the graph like a jug. So the pink part is concave down, the yellow part is concave up. There's something called a point of inflection, where the graph switches from going from concave down to concave up, and that's what we're going to be learning about in the next section. So we're going to learn about how the second derivative relates to whether the graph is concave up or concave down and how to find the points of inflection. Thanks for watching, and I'll see you in the next class.